I'm not sharing the screen. Oh, second please. Okay. So we did it till this point, which is the closest approach. Okay. I'm gonna go forward from this. So when you basically look at like this, so what you need to understand is that here, when you want something to be like this, you give kinetic energy, so the equation would be that there will be loss of kinetic energy, and that would cause, or that would result into gain of potential energy, because it's going closer to that, right? We already know that the equation of kinetic energy is half mv squared, and the gain of potential energy is kq over r. Alright. Now, why is that? Because I told you that this is the work done in the first place, right? So we wrote it like this. Now we can add into this equation. So we know that half, and the mass that is traveling with kinetic energy is 4. So that's 4u, and the speed is 3.0 times 10 raised to 5 whole square. K value is 8.99 times 10 raised to power 9. The charge of the first is basically 2 times E, and the charge of the second charge is 79E. So this is basically the elementary charges that is given. And what you need is that how much closer they're gonna get. So we're going to find the distance of the closest approach, which is D. Now, so to convert it into kgs, we need to multiply 4 with 1.66 times 10 raised to power minus 27 kilograms, and then you got that is the same 3.0 times 10 raised to 5 whole square. This is going to be 8.99 times 10 raised to power 9. This is going to be 2 times 1.6 times 10 raised to minus 19. That's the value of an elementary charge, and then multiplied by 79 times 1.6 times 10 raised to minus 19, and divided by D. So use your calculator, put D there, divide the whole thing here. So you will basically end up with D as 6.05 times 10 raised to power minus 11 meters, and that would be the closest approach distance, or the distance that is between these two charges. Is it clear, everybody? Now, remember, just write a note here. You can check the calculation, please, and if there is a problem, let me know. So if the speed is increased, I mean the initial speed, then fusion can take place. Fusion is basically like they can touch each other and they can then combine, right? So that for the fusion, you must understand that this charge and this charge should actually touch each other like this. Okay, when we're going to look at that too. If you have any questions, please let me know. Okay. So then let's do another type of example that might be there. So it says, given that the diameter of deuterium H21, it's a isotope of hydrogen nucleus, is 2.0 times 10 raised to a minus 14 meters. It says calculate the velocity required for them to fuse. So basically what they want is, they're saying that okay, there is a atom of
So
these.
for them as in two nuclei?
Yeah. They've shown the diagram actually. One is moving, one is stationary, and they want them to basically fuse, mean they want to touch each other like this. If this is the center, then this would be the R, and this would be R as well, which means this distance between them is the diameter, and we want to find this, right? And basically this would be the closest approach. Okay, now we'll do the same thing. We understand that basically the loss of kinetic energy will basically result into gain in potential energy. Okay, now so if that is the case, then we can make two equations. Just give me 1 second, please. Okay, so it's basically half mv squared equals to kq over r. So now we'll do half times 2u. 2u is basically 1.66 times 10 raised to minus 27, and the velocity is required. K is 8.99 times 10 raised to 9. The charge on both of them is 1e and 1e, so we're going to multiply 1.6 times 10 raised to minus 19 times 1.6 times 10 raised to minus 19, so they're two charges of the same value, divided by the closest distance that they're going to get is the diameter, which is 2.0 times 10 raised to a minus 14 meters. So when you do that, you should end up with 1.9 times 10 raised to a 6 meters per second. Is it clear, everybody? Let me know if you have a question, okay? Now, the last type of question is another type of example. Let's try to do it, and then we're going to look at some of the questions from the topical. So it says a positive charged particle moving at a speed of 1.0 times 10 raised to 5 meters per second has a charge to mass ratio of 2.74 times 10 raised to power 7 charge per kg, coulombs per kg, okay? Now it says if the charged particle is directed towards another positive charged stationary nucleus at plus 500 volts. Now determine if fusion can occur. Okay, so this is the question. So they've shown the diagram. There's a charged particle here. There's a charged particle here. They say it is moving at a speed of 1.0 times 10 raised to 5 meters per second. The charge over mass ratio of this is 2.74 times 10 raised to 7 coulombs per kg. And this is the stationary one. And this is at 500 volts. Is it clear, everybody? All right, now we're going to use the same thing but in a different manner. We're going to say, okay, the loss of kinetic energy is the gain in potential energy, but mind you that there is no charge for the other particle, there's just potential. Okay, what we know about this is that of course we need half mv square, but here we're just going to look at the change in potential times the charge. But because this particle which is coming from wherever, when it gets to this potential, it is going to have a change of 500, and we need to know what exactly that would be. So what I'm going to do is I'm going to multiply 2 there. So it's going to be mv square equals to 2 times change in potential times charge, and then I'm going to multiply divide the mass on the other side, so it's going to be mass, and then I'm going to take the root. So when I take the root, I'm going to get the velocity, that's this divided by the mass. Now as you can see that in this question you got charge over mass and potential and 2. So what you're going to do now is that I multiply 2, the potential was 500, and the charge to mass ratio is 2.74 times 10 raised to power 7. So do not worry if they have not given you the values, ultimately they will end up with this. Now when you find this, you will get an answer of 1.65 times 10 raised to 5 meters per second. So what you understand is that this is the velocity that is required for fusion, right? However, and write it, velocity required for fusion, because if you want to get to that potential, that means they will touch, right? And if you're not getting to that potential, they won't touch. So this is the velocity required, and since the velocity that we have is 1.0 times 10 raised to 5 is much less than 1.65 times 10 raised to 5, so no fusion occurs. Do you guys understand this? Okay, Aman, Ratika, Saman,
Yes.
everybody understands this, right? Okay, very good. Now and that's actually very nice. So basically now we have this idea that okay, we have to compare the velocities and the end, right? So now I just want to conclude this chapter by writing an end note before we do some examples from the past papers. So the end note of this whole thing is that whenever you're going to find, you want to find the voltage of a charge, remember the voltage or the potential is the same formula, but for a negative charge, you have to put a negative value. So this will give you for negative potential, and that keeps increasing till it becomes 0 at infinity. So for the negative, 0 is the maximum number. And for a positive one, you just add the positive value of charge. And this would mean that for positive potential, that keeps decreasing because it is a higher number till it becomes 0 at the infinity. So at infinity, the potential is always 0. So you guys need to remember if I draw a drawing. So for a positive one, for a negative one, suppose this is the line of infinity, then this is the field. Then we must understand that for positive, if you're going towards the infinity, this is infinity, so potential becomes less positive, and when you go here, like from negative potential, so potential becomes less negative. Is it clear, everybody? Okay.
Yes.
Very good then. So this chapter has ended here, and now we'll just look at some of the questions.
Sir, for the previous question, can you please show the working? Because I'm getting a different answer.
This one, okay.
What one? Not this one, the previous one.
Okay.
Yeah, this one and the first one.
Okay. You getting a different answer?
Yeah.
Okay, let me see why. Shouldn't happen though. Wait. So this is going to be, first I need to do this, sorry. 8.99 times 10 raised to power 9 times 1.6 times 10 raised to power minus 19 times 1.6 times 10 raised to minus 19 divided by 2.0 times 10 raised to power minus 14. Okay. And then this divided by 0.5 times 2 times 1.66 times 10 raised to power minus 27, and then you got to take the root. You getting this answer?
Yes, sir.
Yeah, probably my calculation is not correct here. Okay, let me correct this. This would be then 2.63 times 10 raised to power 1, 2, 3, 4, 5, 6. Okay, done. All right, anything else? Other things are correct, right? Okay, fine. So let's now look at some of the questions, okay, from the exam papers. I'm gonna go at, let me see where the electric fields are. So I've already given the worksheet for this. How many people have basically tried to do it? Do it, sir. Radhika, you have done that, right? Okay. So now you guys have 1 week, okay? Saman and Hassan Atiq, Aman. You guys need to complete that worksheet, okay? I wanted to do basically this question first. It's a very good question, actually. I'll show you where the worksheet is. Okay. Now, so when you guys go to the classroom, so everybody is in the classroom, you'll see that in the classwork, I have basically submitted electric fields worksheet. Okay, it was on 3rd September, right? So I want you guys to complete it before the next class. That's the one on Monday. Okay, so please do that. Now, so in this question it says 2 point charges A, B have a charge of this, and they're separated by in a vacuum by a distance of this, as you can see. It says point P and Q are situated on a line AB, which is 3 centimeter from charge A and B. So first of all, they want you to find the force of repulsion between charges A and B. So basically that is pretty simple. You just need to use the Coulomb's law, which is K Q over R square. So this will be 8.99 times 10 raised to power 9. The charge for the first one is 6.4 times 10 raised to minus 19. The charge for the second one is 6.4 times 10 raised to minus 19, divided by R is the distance between them, which is 12 micro. Micro is 10 raised to minus 6, and then whole squared, like that. So when you calculate this, basically it is a good idea to use the natural display calculator. Okay, the one I have, you'll find it in the market if you don't have it. Basically it helps you a lot and make like less mistakes. Then minus 19 times 6.4 times 10 raised to power minus 19, and then divided by 12 times 10 raised to power 6, or minus 6, sorry, minus 6, and then whole square. So basically that force of repulsion got to be, well, that's pretty small. Why is that? The charges are big. Shouldn't be that small, right? Okay, never mind. So that's 2.6 times 10 raised to power minus 17 newtons. Is it clear, everybody? Any questions? Let me know. Okay. All right, so now let's go to the next question. In the next question, it says explain why without any calculation when a small test charge is moved from P to Q, the net work done is zero. So what they're saying is that if I move a small charge from P to Q, the net work done is zero. The point is that if you look at it, both charges are of equal value and they're repulsive as well. So whatever the potential here is, all right, that would be the same potential here. So when you move from here to here, basically the change in potential will be zero. And if the change in potential is zero, then according to the work done equation, which is change in potential times charge, then the net work done is zero, right? So we're going to say as both charges are of same charge and sign, right, the change in potential will be zero at from moving from moving P to Q, right? Hence work done will be zero, as work done is change in potential times the charge. Is it clear? So that is the thing you could write. And they have the same distance as well, so that's fine. Now they say calculate the work done electron moving from midpoint line AB to point P. So if something moves from the midpoint would be basically 6.0 micrometer from here and 6.0 micrometer from here, and it wants us to move from this to P, so it will move from P, and the charge is an electron, which is this. Okay, now whenever you're moving and they want you to find the value of charge, work done, or potential. So first of all, let's call this point M. Okay, so the best thing is that you will first find the total potential, the net potential at M. So how would we be able to find this? So because M is a point that is affected by A and B both, so what I'm going to say is that the midpoint M is affected by A, and the potential that is at M due to B would be the total potential at M. So how do you find this? You use K Q over R plus K Q over R. Both are the positive charges, that's why it's positive. So then what you're going to do is you can take K common, so that's 8.99 times 10 raised to power. In fact, both charges are same, so we can also take that common as well. Okay, then you might be confused, so we don't want to do that. 6.4 times 10 raised to power, I think it was minus 19 divided by the distance is basically 6 10 raised to power minus 6 plus 6.4 times 10 raised to minus 19 divided by 6 times 10 raised to minus 6. So 4-mark question would require some work. Okay, so when you do that and take out the calculator, while I'm doing it, it's best that you guys also do it. That way you will be able to catch me making a mistake, and then you can just add this 6.4 times 10 raised to power minus 19. Here 6 into 10 raised to power minus 6 plus 6.4 times 10 raised to power minus 19 divided by 6 times 10 raised to power minus 6. So the net potential here will be 0.00 1, 9 and 2 volts. Okay, so we got this answer, and then we will find the potential where it moves. So it moves at P, so at P we're going to write the potential at P due to A plus potential at P due to B, right? So if I write an equation for this, so it will be going to be, sorry, I need to write here, KQ over R plus KQ over R. K is the same, so we're going to write 8.99 times 10 raised to power 9. Here we're going to get Q, so the charge was 6.4 times 10 raised to minus 19, but the distance of A from P is 3, not something else. So we got to take 3 into 10 raised to minus 6 and plus 6.4 times 10 raised to minus 19, and the distance of B from P is basically this much, which is 9, I believe. So that's going to be 9 times 10 raised to minus 6 whole square. So now let's try and find this. So I'm going to use the same calculation. I'm going to just change this to 3 and this to 9. Nothing else really changes, right? So this would give me 0.00256, okay, volts. Then what you're going to do is you're going to find the change in potential. Always do larger minus smaller, because this is a quantity, scalar quantity. So larger value is 0.00256 minus 0.00192. So minus 0.00192. So we get the answer as 0.000637 volts. Now you might be wondering for this long question why they were given us this much area. Basically in an actual exam you will have a larger area, since this is a PDF, they've shrunk it. Don't you worry about it. Now to find the work done is change in potential times charge. So we got the change in potential, and then the charge in electron is basically 1.6 times 10 raised to power minus 19. I'm going to multiply this answer with 1.6 times 10 raised to minus 19, and we're going to get like 1.02 times 10 raised to power minus 22 joules.
Sir, I was trying to tell you that the first question which we did, even that was wrong. The answer was wrong.
The first question, which first question?
The one which we did in the notes, but I guess you didn't hear me.
Oh, okay. My bad then. I make sometimes, calculation errors. Can you tell me which one?
Sir, the green one.
The green one?
Yeah.
Yeah, what was the answer here?
1 sec. It was 1.22 into 10 raised to minus 10.
Minus 10. Okay, that would be the answer then. 1.22 times 10 raised to minus 10. Okay, fine. Alright, thank you then. Now, so this was the answer. Okay, you guys have any questions regarding this? You guys understood everything what I did here?
Yes, sir.
Okay. Now, so these questions are like the same as, in the gravitational fields you do the same, in this you do the same. It's not a big difference really. So now let's go to well, this is a curve. This was the electric field strength question. Okay, this is the question this is a very similar question to what we did, right? Where it says a specific charge per unit mass is given, see, charge per kg, and then potential of metal sphere is given, and then they say use the expression to determine the particle reach the surface of the sphere or not, right? We've just done the same type of question in the last one, right? So that's not a big deal. Now, what else I want to do? Wait a second. This one. Okay, I want this one. So when you will complete the worksheet, you will find these questions, a lot of these questions, and it'll be pretty, feel like it's easy. So for for question number 7 here, let's look at it. It says an alpha particle and proton are at rest at a distance of 20 micrometers apart in vacuum. It says state the Coulomb's law. So the Coulomb's law is basically that force is directly proportional to the product of charge, and force is inversely proportional to the square of distance between them. So that's what you need to write, but in words, not like me, okay? Alright, now let's go forward. So then says the alpha particle and the proton may be considered to be point charges. Calculate the electric force between. So this is pretty simple. You just need to do F equals to KQ over R square. Now K in here would be 8.99 times 10 raised to 9. By the way, alpha particle, you should remember, it's basically the knowledge from AS that you should know, that alpha particle is a helium nucleus, and helium nucleus is 4 and 2. And what else is there? And a proton, and proton is basically 1 and 1. So the charge on helium nucleus is 2 times 1.6 times 10 raised to minus 19, that's 2e, times the charge on proton is 1.6 times 10 raised to minus 19, and then divided by what do they need? The distance, right? So distance 20 micrometers. 20 times 10 raised to minus 6 whole squared. Sometimes I also forget about it. Okay, so then you just need to write 8.99 times 10 raised to power 9, and then multiply by 2 times 1.6 times 10 raised to power minus 19, and then 1.6 times 10 raised to power minus 19, and then divided by 20 times 10 raised to power minus 6, and then you take the whole square. This is going to be 1.2 times 10 raised to power minus 18, okay, newtons. So that's pretty simple. Okay, so then it says define electric field strength. So electric field strength for 2 marks is defined as the force per unit charge. That's the main definition for the first mark, and for second mark you always write for a positive charge, or you could just write that it's force per unit positive charge. That would also give you 2 marks, okay? Remember that, because we take positive charge as a reference, okay? Now here they say point P distance of particles along, and both of them they've shown this, right? Now they say the variation of the distance x electric field EP due to the proton above. Explain why two separate electric fields have opposite signs, right? So first of all, I want to tell you that basically this is a positive particle and this is also a positive particle. So its directional electric field is this way. So if I say this is the electric field of alpha particle, and the positive field also goes out of the proton, so this is the electric field of protons. So basically this is a vector quantity, and right now where they're comparing at point P, you might see that they basically are in the opposite direction, right? So what I'm going to write is here, how in marks? 2 marks. So for 2 marks I'm going to say that electric fields are in opposite direction since they are vector quantities. Hence, negative sign. Is it clear, everybody? Like that. Now, keeping that in mind, then it says sketch the variation of X of combined electric field due to alpha particle and proton for this 4 micrometer to 6. So we have already done it in class, but I'll do it again. So till 4, basically you're gonna start with you're gonna see where exactly they basically have the same value. So if you look at it, at 12 they have the same value of electric field strength, like it's 2 boxes above 2 boxes. So this is the point where they're going to be 0 electric field strength, really. And now you just need to draw a reasonable, like start from here, make a curve that passes like this. Okay, this curve is not correct, it should be like this, and then from on this side it's gonna go up, and then line would go closer till it reaches to like this. So this would be the net electric field. When you add both of them, that is the same thing. But remember, because I chose this point, because the value of this in negative and the positive is the same, so I chose that this is the point where electric field strength will be 0. That's why I put the cross would happen here. Is it clear, everybody? Any questions? Alright, so I have given you the worksheet. I hope in the next class when we see each other on Monday, it would be there and I will check it. So you need to submit it. I don't want pictures. So what you guys gonna do is you're gonna download Cam Scanner. Cam Scanner, take pictures from Cam Scanner of your work if you're not doing it digitally, and then make a PDF out of it, and then you upload it on Google Classroom. Alright, so I hope to see you then in the next class. Bye.